In this video, we are going to extend the pipe flow simulation to a flow over a backwards facing step in order to then get a streamline visualization showing the created vortices. Let's get started. Hi and welcome to this new video. As we've seen in the intro, the result of our simulation will be a streamline plot, as you can see here, and depending on the Reynolds number you choose, you will have a vortex here right after the step, which is situated in the bottom left. And if you go for higher Reynolds numbers, you will even see a second vortex being created right here. And this can all be visualized. So let's start modifying our pipe flow scenario. Okay, here we are. Now the docstring has changed, but right below the docstring, we have the same code that we've written together in the video on the pipe flow with inlet and outlet. So if you want to fully understand what's going on in this video, I would advise you to go back, especially because this last video used the staggered grid, which is a little bit mind-bending if you look at it for the first time. And here we will just base upon the implementation that we already have and just modify it in the spots where we need to do. So as said, this is the code from before, which we're going to modify, but let's first look a little bit at the changed scenario. So here again, we will be solving the Navier-Stokes equations. So it's again fluid motion that we are solving. And we will again be using the staggered grid. And remember, we needed a staggered grid in order to avoid these pressure oscillations that can happen in these particular interior flow scenarios. Then we will use a finite differences approximation of our differential equation. We have an explicit Euler time stepping for simplicity here, and we will use a so-called P2 pressure correction scheme, which has a high similarity to the simple algorithm that you might have seen. Remember, the big difference between the P1 and the P2 pressure correction scheme is whether the pressure gradient is included in the momentum equation. And as said, our scenario has changed a little bit, so let's look at that. So we again consider some sort of a pipe, at least you can think of that. So we have a rectangular domain, so it is longer than it is wide in that sense. In the top edge and the bottom edge, we will again have wall boundary conditions. This means we will prescribe the velocity to be 0 in both directions, just directly on this boundary. And then we have our step. This one is new. It is in the bottom left of our domain. And essentially, we can think of it as just a part of our domain where no fluid is allowed to flow through. And so this also means that we will prescribe wall boundary conditions right above the step and also on the right edge of the step. And then again, on the right edge, we will have our outflow with the outflow assumption, which means that the normal derivative, so this means alongside the x direction, is 0, and that's because our flow has fully developed, meaning that it does not change anymore over the x-axis. And then on the left we have an inflow again, but here you have to be careful that in this particular scenario here, the inflow is shorter than the outflow, and we will consider a uniform inflow profile. So this will just be horizontal arrows of same length entering our domain. And then we already saw the streamline visualization. I just want to show this here once again. So at first, right above the step, we will have a similar thing as we've seen with the pipe flow. So the Hagen-Poiseuille parabolic profile is getting developed, which means that our flow is changing from a uniform profile to a parabolic profile. And this development should almost be done up until it reaches the end of the step. And then since our diameter widens, our fluid tends to use the entire diameter of the pipe. And the interesting thing is that at certain Reynolds numbers, this will result in a backwards flow right behind the step, which means that our flow tries to have streamlines that go, for instance, from here a little bit downwards to then be in the center of our wider diameter. And this results that at certain higher Reynolds numbers, we have a backflow which will create these vortices here that you've seen. And I've also indicated in the second spot that at higher Reynolds numbers, you will also see vortices here. And then after a little longer in our domain, our flow will be fully developed again, and will again have the parabolic profile that we also saw in this previous pipe flow video. And then our flow just exits domain at the outflow boundary condition. And of course, we have to consider for the step in our computational mesh, and we will look at it in a really simplified way. So this will be a little bit hard to digest, so bear with me. So we will again have our top boundary here. And remember, we are in a staggered grid, which means that our unknowns are not saved directly on the vertices, but rather they are staggered. So the pressure is found inside of a cell, whereas the velocities are found on the edges to which they are perpendicular, which means the x velocity or the u velocity will be on this face of the cell, whereas the v velocities will be at these faces of the cell. And the reason we did that was to avoid the pressure oscillation, because now when we want to compute the divergence and the pressure gradient, we would not exclude the point itself for which we would compute the gradient. And the difference to the pipe flow now is that our domain has some sort of an L shape in that particular case. And for simplicity, we will keep all the degrees of freedom in the bottom left that are part of the step, but we will just do some small modifications in order to not have them active during our simulation. So in other words, during each time iteration, we will actively set the degrees of freedom in this step to 0. And of course, we have to account for the additional boundaries that we get. So the boundary right above the step and also the boundary to the right of the step. And since we essentially keep all degrees of freedom in compared to the pipe flow scenario, our arrays that we will be using have the same shape. So in this particular scenario, we will have u velocity that use an ny plus 1 by nx number of nodes, and the v velocity use ny by nx plus 1 number of nodes, and the pressure, they have ny plus 1 by nx plus 1 nodes. Okay, let's try to modify our file according to the changes. So let me go down here, and first we have to modify a little bit our constants that we have for the simulation. So first of all, I want to have a wider aspect ratio. So I want this to be 20. And you will see here to the left, that's because of the Git versioning I have here. You see the lines where I modified the file. Then I also want to increase the number of time steps to 60. And I want to plot every 100 iterations. Then of course we also need to define the size of the step. And I just want to have this quite ad hoc here. So we will use a step height in number of points to be 7. So we will have 7 discretization points in the height of the step. And since we use 15 discretization points in y direction, this is approximately half of the length in y direction. And of course I have a typo here, this should be step height. Then we will have the step width in points, and this one I want to have for 60. Okay. Then we of course have to modify the initial condition. So because we said that we want to initialize our flow only that the values above an imaginary line over the step, so right above this where I marked here, shall be 1. So this should be a uniform profile. And then in the bottom right here, just behind the step, we want to have also a 0 component in x direction. Okay, for this, let me go down to where we initialized our velocity field. So let's say initial condition. And for the velocity x previous, we have to modify that so we can keep the ones here, but then we have to modify everything that is below the step. So we'll do velocity x previous, and now we have to cleverly access that. So we have to say from the beginning, so from y equals 0, so the bottom line, all the way to step height points plus 1, and then all values in x direction. And of course we use the plus 1 here, maybe look at a space, since the ranging in Python is excluding the last element. So this basically means except for the step height points. And this one should be 0. And I will also show this to you in the staggered grid real quick. So if we go up here, then we look at our x velocities. So this is velocity 0 component, so 0 in y, then 1 in y, 2 in y, and 3 in y. And here in this setup, we have a step height of 1, 2, 3. So we would be indexing from 0, 1, 2, 3, but excluding the last element, which essentially gives us all those. And this is essentially how we want to initialize them. Okay, well, let's go down and go on with our initialization. So this will be as said. This will be everything in the interior. Then of course here this would be our bottom edge. So let me move that a little bit down and first have the top edge, because the top edge will stay the same. There is no modification with a step at the top edge, so we can keep this one. And again, remember that we set the velocity just outside of the domain, so the ghost value, to be the negative one inside. And the reason for that was that then on average, our velocities on the boundary will be 0. Because if you take the ghost value and the interior one, average them, you have the value on the boundary. And if the outside value is exactly the inside value, then this average will turn out to 0, which is what we want to prescribe for our wall boundary condition. Okay, so let's keep going with top edges, because now we also have a top edge of the step. And here we have to set the value of the x velocity array just below the step. So essentially we have to set this array, and we want to set this array to be the value of the one that is inside of the domain, but negative, such that we then again have the average being 0. So let me go down, and then we have to say velocity x previous indexed at the step height points. And this makes sense. Maybe we can take a look at it once again. So because now we have 0, 1, 2, and we have a step height of 0, 1, 2. So this will be these velocity x values. So let me go down and say this is step height points. And then in x, we have to go from 1 to step width points. And we do from 1, we exclude the 0 element, since it will be like this corner one, and we are going to set it by the help of the inflow later on. So we will have the step width points, and here let's check that again. So this should be excluding this one. So we have 0, 1, 2, 3, 4, and then 0, 1, 2, 3, 4. So we will exclude this element because this one is directly on the boundary, and we can then set it by the help of the right edge. Like this, it's a little weird here, the highlighting. So we will just do essentially those 3, excluding the 0th one, and then also setting this one in the right edge of the step. So let me go down, and here we will be having, okay, this one. And now we want to set this to be the negative values of right above the step. So minus, and then velocity x previous indexed almost similarly, but now at step height points, maybe in brackets, plus 1. And then here we have again 1 to step width points. And maybe let me move that into the next line. So this is the top edge of the step. Let's do the right edge of the step. And here we say velocity x previous. And now we have to do a range-based indexing on the y coordinate. So this one will be from 1 all the way to step height points plus 1. And then on the x coordinate, we will be on step width points. And we can check that if we look at our schematic again. So now we want to index the points on this one here. Let me highlight that real quick. So here, this right edge. And for this, we don't want to set the value that is in the ghost cell below our domain, but only the values that are directly on the right edge of the step. And if we count, so our step here is 0, 1, 2 in height, and we want to index from this, so this is 0, 1, and we want to index 1 and 2. So we do a range-based indexing from 1 to 3, because the last element is excluded, and we don't want to modify this element. So let's go down, and here we are at the right edge of the step. I will again go into the new line, and this one can be directly set, so probably we don't need the new line. It can just say this is 0.0. And then we have the bottom edge of our domain. And here in that particular case, we already had something for the bottom edge, but we have to be careful because now our bottom edge is essentially a little smaller because of the step. So we can just modify what we have. So this is the bottom edge of the step. So not of the step, of the domain, of course. Then let's go up and let's look at our schematic. And here I want to set the value that is a full part of the bottom edge. So not this corner value basically, but the values that are here. So that go from the step width +1 all the way to the end, but excluding the last element. So because we also don't want to consider this corner node here. So in essence, we then have to modify our indexing on the X. So we will keep 0 point on the Y, and on the X, we have to index at the step width points +1 all the way to the last element, but excluding it. So going to -1. And then this will be set to the negative value just inside of the domain. Same idea with the averaging again. So we will have step width points +1 to -1. And let me put that into a new line. And then we just have to set the values inside of the step. So this will be the values inside of the step. And here we have to be a little bit careful because inside of the step, there are like 2 layers basically. We have those values that are technically inside of the step, but are part of ghost cells for prescribing the boundary conditions on our step or the wall boundaries of our step, particularly this line here. And then also we have this vertical line, but then we also have the values which are fully inside of the step. So essentially those, and these will just be set to 0. And of course we do that because we have our structured grid and can use these fancy arrays in NumPy. We will be setting all the values here first in X to 0. And these, for this we have to index them from the beginning to the number of points in X and Y direction, because they are then excluding them. So because here we would have 0, 1, 2, index in Y direction, and we only want to set for 0 and 1. So we will do an index-based looping from 0 to 3, or from the beginning to 3, and this will then exclude the last element. Easily this can be implemented in the following way by saying velocity x previous from the beginning to the step height points, and then from the beginning to the step width points will be 0. I mean, this technically would not have been necessary since we already allocated them, set them to 0 here, but that should be fine. But it's just to have that here. The creation or the initial condition for the y velocity will be identical. I mean, it's just a 0 away. The same for the pressure. Okay, let's go down to our time loop. But before we go there, let me first modify the figure size a little bit. So I want to have this 15 by 6. I mean, you can also keep it the way it was before. Okay, and now the super nice thing is that the diffusion, the convection, the pressure gradient, this will all stay the same. Also the update routine with the explicit Euler step. The only thing that requires modification is the boundary conditions, or are the boundary conditions. And the interesting aspect is that we can mostly copy what we already had. I just want to write it down once again so that we get the feeling for it. So I will first maybe, get this a little bit down and first start with our inflow. And for this, we just directly prescribe the values on the left boundary right above the step. So velocity x tentative, so because we are now in this tentative step, indexed at the step height points +1 all the way to the last element, excluding the last element, because we will see the very top element in the ghost layer as a way to prescribe our wall boundary condition. And then of x, we are of course at 0, because this is the value just on the boundary. Let me show that to you again. So in essence, these will be those values here directly on the boundary, so we can directly prescribe the 1.0. Then we will have our outflow boundary condition, so outflow on the right edge. So let me say outflow, and here we will say that our velocity x tentative, and here we go from 1 to -1. So because we go from the, not the very first, so the 0, but the first element all the way to the last, excluding the last, and then all the way to the right, because this is setting the values on the boundary. And this one shall be the values one element inwards of the boundary. So velocity x tentative, 1 to -1, and then -2. And the reason, of course, is that this is then defining a zero gradient or a zero derivative. Because note, it's not a wall boundary, so we're not using the negative value, but we're using the identical value. And maybe you remember from the last video when we prescribed the outflow boundary condition after the incompressibility projection, we did this, let's say mass flow correct, because we have overall continuity in our domain. So the mass that enters our domain has to exit it. And we will do the same thing now with the tentative step as well, because it tends to be crucial, because here we don't have an evenly sized input and output. So because the input is smaller or the inflow is smaller than the outflow is. Okay, let's try to implement that. And for this, we first have to compute the inflow mass rate tentative, or after the tentative step, by being the summation over the velocity x tentative accessed on the inflow, which will be the step height points plus 1 to the very last element excluding it, and then in x direction at 0. And the outflow mass rate tentative is going to be numpy.sum on velocity x tentative, and here we index from 1 to -1 and then at -2. So the second to last, which we're also using here to set the velocity right on the boundary. And then we will just multiply this with the ratio of the inflow mass rate tentative divided by the outflow mass rate tentative. And let me move that into the next line. Then we have the top edge of the step for a wall boundary condition. And here we say velocity x tentative. So we have done that kind of before by y being step height points. So to define the ghost layer inside of the step, and then 1 to step width points in order to have this indexed, the ghost layer. And this one shall be the negative value of velocity x tentative right inside of the domain. So at step height points plus 1, and then the x being indexed again from 1 to step width points. And then we have the right edge of the step, right edge of the step. So we have velocity x tentative at 1 to step height points plus 1 in y direction, and in x direction at step width points is going to be 0, because we are directly on the boundary again. Then we will have our bottom edge of the domain, and here we'll say velocity x tentative at 0 in y direction, and then step width points plus 1 all the way to the last element excluding it is going to be set, and let me go to the next line, the negative value of the velocity x tentative inside the domain. So velocity x tentative 1, and then step width points plus 1 all the way to the last element excluding it. And then we're just left with the top edge of the domain. And here I will just copy this one. So this should be, I think that's that one here. Yes, that should be this one here. So let me copy this. This will just set the top edge of the domain. Then we can delete this one here. And this is the boundary prescription for the velocity in x direction. Let's check similarly for the velocity in y direction. So here this will also take us some time in order to get this down properly. And here I want to also start with the inflow again. So we will have the velocity y tentative on the step height points plus 1 all the way to the last element excluding it, and then 0 on x. And here we know that since we have this staggered grid, let me remind you of that in this particular case now the y velocity is outside of the domain or on the ghost layer and not directly on the boundary. So we will use an averaging again, and since we want to prescribe it to 0, since we don't have a y component of our inflow, this one is the negative inside value, similar to what we would also do on a wall boundary condition. So let's get down and have this written. So this is then velocity y tentative, or better the negative value of velocity y tentative at step height points plus 1 all the way to, here we go, to the last element, excluding it, and then 1 to have it right inside of the domain. Let's check on the outflow. And here again, similar idea. Now our y velocity is not directly on the boundary, but here for the outflow, we want to prescribe a Neumann boundary condition. So we will just take not the average, but the difference shall be 0. So the value on the ghost will be the value inside of the domain. So velocity y tentative from 1 to -1 in y direction. And then the last element, so the ghost layer, and this one will be velocity y tentative 1 to -1 at -2. And this should then set the Neumann boundary condition to be 0. Then let's move on with the top edge of the step. And here we are velocity y tentative. And now since we have a horizontal boundary, our velocities in y direction are directly on this boundary. So in y, we will be at step height points. And then in x, we go from 1 to step width points plus 1. And we can directly set that 1 to 0. And I also want to show this to you in the schematic. Basically, what we're setting here are these values now. And in order to include this point here, we have to go one step ahead because Python has this range-based indexing that it excludes the last element. So let's go down and continue. So this was the top edge of the step. And then we will have the right edge of the step. And we will say velocity y tentative. And in y direction, we will index from 1 all the way to the step height points plus 1. And then in x direction, we are directly on the step width points. And this one will then be the negative value of these inside of the domain. So velocity y tentative at 1 to step height points plus 1. And then step width points plus 1. Or maybe let me also put this into brackets to have this a little more beautifully. And here we go. This is the right edge of the step. So now we should just be missing the bottom edge of the domain and the top edge of the domain. So let's first have the bottom edge of the domain. And again, horizontal edge. So our y velocities are directly on the boundary. So we will have velocity y tentative at y and 0 and then step width points plus 1 all the way to the end should be directly 0. And I can show this to you. So this will be these particular values here. And we will exclude this last one in order to continue prescribing the wall boundary condition. But it is not particularly relevant since it's one of these edge elements. But the crucial thing is that those are directly on the boundary. So we directly prescribe the wall boundary to them. So let's go down. This was the bottom edge. So let's move on to the top edge of the domain. And this is velocity y tentative at -1. And here then we take all the values in x. And this can directly be prescribed to 0. And then something that I probably forgot for the y velocity to set all, here in that particular case, v velocities to 0 inside of the edge. So this will just be velocity y tentative from the beginning to step height points, from the beginning to step width points shall be 0. And probably we need this for the boundaries in x as well. Yes, I thought so. So this one will then be set all u velocities to 0 inside the step. So velocity x tentative, that's easy to confuse here, from the beginning all the way to step height points, from the beginning all the way to step width points should be 0. So these were the boundary prescription for the tentative step. Let's do something similar for the pressure. In our pressure correction problem, so this elliptic problem we are solving here for the pressure correction, we also have boundary conditions. So these are kind of some artificial boundary conditions. And we said we have homogeneous Neumann boundary conditions everywhere except for where the outflow of our domain is. But now, of course, we have to account for the step. So well, let's try our very best here. So let's move that down as well. And we will first start with the inflow, or basically the left edge right above the step. And for this, we will have pressure correction next, indexed at step height points +1 all the way to the end, excluding the last element at 0, is then going to be the pressure correction next right inside of the domain. And by doing so, we will obtain a 0 Neumann boundary condition here. I will also show this to you real quick. So here again, we see the circles indicate pressure nodes, and we want to have 0 Neumann on all the boundaries, except for the right, where we want as 0 Dirichlet. And for this, we will take just the first derivative approximation of our Neumann, or of our pressure nodes, and then this gives us the derivative value right on the boundary, and we set it to 0. And if we rearrange, this would yield that the outside value is equal to the inside value. Okay, let's go down. So this is the inflow. Then let's have the outflow. And here, as said, we want to have a 0 Dirichlet. So let's do pressure correction next, indexed from 1 to -1 at -1 to get the ghost layer. And this one shall be the negative of the inside value now, in order to get a 0 Dirichlet by means of the averaging. So we will have this one here. Then let's move on with the top edge of the step. So let's have pressure correction next, indexed at the step height points, and then 1 to step width points +1. And we will set this one to the value inside of the domain. So pressure correction next. And I mean, you kind of see a pattern here, just to have a small break, that whenever we do these indexings, when we set them to the values inside of the domain, we will add 1 or subtract 1 from the index location where we only have 1 integer, and we keep the range. So the range stays the same. Here this then means we have the step height points +1, and here we will have 1 to step width points +1. This was the top edge of the step. Now let's move on with the right edge of the step. So I think you see this is kind of a little bit repetitive, probably also not too interesting. It's a little bit mangling with the indices in NumPy. Although I think it can also be extremely insightful. So let's have pressure correction next, indexed, and now we are on the right edge. So we have a range-based indexing in y direction. So from 1 to step height points +1, and then in x direction we are directly on the step width points, and here we then have our pressure correction next, and again we keep the range-based index, so this will be again 1 to step height points +1, and then we will increment the step width points by 1, so this will be step width points +1. So this is the right edge of the step. Next up we have the bottom edge of the domain. So here we have our pressure correction next, and in y direction we are at 0, and in x we will be going from step width points +1 all the way to the last element, excluding it, and set this equal to the pressure correction next at 1. So this one is incremented by 1, and here we will then have the same range space indexing. Here we go. Then we are left with the top edge of the domain. Let me scroll down a bit, and this one shall be then pressure correction next, indexed at -1 in y direction and all values in x, equals pressure correction next at -2 and all values in x. And then, of course, what I forgot with the u velocities, to set all pressure, maybe also correction values inside of the step to 0. So we will have pressure correction next, and then indexed from the beginning to the step height points, from the beginning to the step width points shall be 0. And then we can remove the prior boundary prescription and we're good to go. This is the boundary prescription of the pressure. Then we are left with the boundary prescription that we had after the pressure correction step. So these are basically those. And here I will just delete what we had and copy the boundary prescriptions that we did in the tentative step and just changed tentative for next. So I want to get this here. Let me copy that and go down here. Where are we? Here it's where we deleted. And then let's also copy it for the y velocity. And then we will have a rather boring task of changing tentative for next. I mean, generally speaking, copy and pasting tend to be error prone. We will see later on whether this is truly the case for us here. So let's just say change next to tent. I will quickly speed that up for you. Okay, here we go. Now everything should be adjusted. We will see. Let's also make some quick modifications in the visualization routine. So first of all, remember that we first had to do our mapping from the staggered grid to the vertex-centered grid. And I just want to artificially modify the values inside the step to be 0, because there might be some glitches from time to time, and by this we can avoid that. So we will do velocity x vertex-centered at the values inside the step. And now we have to be careful that since when we are back on our vertex-centered grid, so let's look at our mesh. So now we have values defined on the vertices. I also want to set the values directly on the boundary to 0, of course, due to the wall boundary condition on our step. So this means we have to do from the beginning all the way to step height points +1. And then in x direction also from the beginning all the way to step width points +1 shall be 0. And I want to have the same for the velocity y vertex centered. Let's change the contour plot a little bit. So here in this particular case, it would also be interesting to look at the negative values. So I want to have a color map going from -1.5 to 1.5. And then we had these vertical lines which showed us the velocity profile. And I just want to move them at some different spots. So this one shall be at 40 now. And the one below I want to have at 180. So here we go. And here we probably also need to change to 40. And here also to 180. And of course, yeah, here we go. So this should be 40 again. And maybe let's have a fourth one. So let's copy this one down and have 80 here as well. So 80 cell length and 80 here. So we have now 5, 40, 80 and 180. And then let's have a little bit of a longer pause in between the drawings. And then towards the end, we wanted to have our streamline plot. So I will just create a new matplotlib figure and then just fill it with a stream plot. So a plot of streamlines with coordinates x, coordinates y, and then here we have our velocity x vertex centered, velocity y vertex centered, which are then taken from the very last iteration. Okay, here we go, the moment of truth. So let's see whether our modifications resulted into any bugs. So I will call Python flow over a step, and here we go, it's running. Hope we didn't make any mistakes, but at least qualitatively it looks good to me. And as we've seen in the intro, we have the step kind of here, so it has 7 elements in height and a certain number of elements in x. So remember that we didn't plot all the arrows, so just a subset of them. So you can see that, where was it here? So we just plotted a subset of the arrows. And interestingly, we kind of see the flow going down here and trying to adjust for the different size here, for the different size and the diameter. And here we have it. So at the very end, we get our streamline plot. Maybe also let me enlarge it a little bit. And here we can see that we have our vertex as expected right above the step, right behind the step. I mean, it's rather a small vertex, so that's also the reason you can't really see it with the arrows of our quiver plot. Something else to notice is, of course, that in the beginning we have our inflow section. So in the very start we have still kind of a uniform profile, which then has turned into a fully parabolic. And then once the fluid is behind the step, it is trying to go to the parabolic profile, which is now centered at the center of our wider domain, but is creating some backflow. And I hope that it is visible in the recording that our line is also inclined just so slightly to the left due to the backflow over our vertex here. But as mentioned, after some time, we have our parabolic shape. Probably we should have run it for a little longer, since we don't have a full parabolic profile towards the end yet, but I would encourage you to play around with it. So let me close that, as well as this one here. And then, as mentioned, you can augment the kinematic viscosity to be lower in order to get a higher Reynolds number, and then also see the other vortices being created. A big thanks to all the Patreons of the channel. If you also want to support my vision of free education on these advanced mathematical topics, you find the link to the Patreon page down in the video description. That's now the end of the video. If you enjoyed this content, then please leave a like and subscribe to the channel. There's more like this on here. You will find similar simulation scripts simply implemented in Python. And Julia, probably this one was a little bit more of an advanced one and also a little bit more of a tedious one, since we had to do all this indexing. And I hope there weren't any errors. If you spotted something, please leave a comment. If something is unclear, also leave a comment. And if you have an extension, then feel free to open a pull request on GitHub. I would be happy to merge in your code to the repo. And that's also where you find this source code file here in case you want to experiment. Here you will now see similar videos like this one, and I hope to see you in one of my next videos.